Hello and welcome. I'm going to go through the steps for doing a Morse fit on your scan results from a potential energy surface scan on something like HCl. Okay, so I'm going to click on the completed job. So we're just in WebMO, hit completed the bond link scan. We scroll all the way to the bottom here and we see our scan results. We had mentioned copying and pasting this data to Excel before, but I just wanted to show again. And I should vaguely apologize for having to shoot a video of a PC screen, kind of running out of time trying to get videos prepared, and the PC that has the Morse fit and the program we need to use to run that doesn't seem to have any video player that can record, so we're making do. So we're just copying this data over to Excel. Should paste into one cell per window. You can see that. I'm going to delete the line at the top. I'm going to try to zoom in a little bit here. But so the idea here is no labels at all for the Morse fit, for the program we need to use. So we don't want any labels, we just want our data. And the only other thing we might do though is try to maybe change the unit of the data. We can also maybe try to zero out the data. So what I might do here is take each of our data points and multiply it by a conversion factor such as 25.5 kJs per mole. And then I can copy down. We can then look for, this might be a little bit hard to do, but we might try to figure out what the minimum value is. You can type minimum, and then from the whole series, there's at least 1,000 data points. Minimum. Did I spell wrong? Oh, maybe it's just min. Yeah, it's just min, not minimum. Okay, and so this is the minimum value. Now, one of the things that's always tricky is, whenever you paste something, you want to paste maybe sometimes the value. So I'm just going to paste the value here so I can copy just the value. And then what I'm going to do is I'm going to take each of these points here and I'm going to subtract the minimum value from each point, and I'm going to copy that down. A few ways to copy down. You can actually copy and then select the entire portion of the cell, paste accordingly. Okay, so then copy right. Oh, it's doing the cell. We want to minus the value. Okay, let's do our other trick. Let's 25.5. Let's put that back to what it was. Let's do the trick where we minus the cell here, then we put dollar signs in front of the E and the 1. What that'll do is it'll lock that cell in to not change, and then we can copy down. Okay, there we go. Now we see our minimum 0.0. So the basic idea, you have a Morse potential, and it's going to increase and plateau off, and then have some minimum point here that's now zeroed out in terms of energy. And now the only thing we need to do here is kind of clean up our work. Copy here. We're going to paste over to here, but we're going to paste the values. And then we're going to delete all this stuff here. So the only thing we have is the table of bond lengths in angstrom and our energies in kJs per mole. Now, to be fair, I can't quite remember the Morse fit file. I'm kind of scratching my head here. It's either written for the energies coming in kJs or kcal, but we can easily, make the other conversion to kcals instead of kJs if that was actually the case. So at this point here, I'm going to do a file. I'm going to do a save as. Or I'm going to, all right, something's not catching up. The expanding. Okay, so what I'm going to do is do a save as, and I need to save this data. I want to get into the browse. I need to save it as a text file. Okay, and not any kind of text file, but a text tab delimited. So this specific file here, I don't know if you can see it, but it's text tab delimited. There's other text files. There's like text Macintosh. There's text, MS DOS. We want tab delimited. So we choose that option, and it's just saving as book 1. Choose a simple name, just nothing real complicated here, and I'll say why. You'll see why in a minute. So book 1, really easy. And then the other thing we want to do is save this somewhere where we know where we're at. And we can try the desktop. Sometimes this works, sometimes it doesn't. We just want to be in a directory where we know what the directory is, so we can easily find the file. So we'll just save it over to the desktop. So some features may be lost. If we had graphs, we're going to lose them. So don't save graphs with a text file. If you close the file, open it, you're going to lose that data. That's what this warning is telling us here. So we do want to keep using this format. Okay, so now what I'm going to do is get to the text file that I need. To do that, we go over to Carmen, get into the course files, and we're looking for the zip file. Spring 2018 is the last time I updated the file. And so we just click to actually download that file. It contains a bunch of stuff. A lot of the stuff we don't even really need anymore. I can probably find a better way to upload some of this stuff. But there's a Morse fit spring 2018 version. We can copy and paste that. I think it's already on the desktop, but we can paste it to the same place where we saved book 1. So there's book 1 over here. I think I hit paste instead of copy. Let me try to move that file from where we were at to here. It's probably going to tell me it's already there. Okay, so I'm going to cancel, use the file that's already moved, because I already moved it over here, and it should just be in alphabetical order. Here it is. And so there's some instructions that I could read through to summarize this information. Is experimental procedure. There's an appendix that describes this a little bit more on the data analysis, but we're going to complete the potential energy surface scan, obtain the energy as a function of bond length, which we have. We prepared our text tab delimited file by having one column bond lengths, the second column as the energy values. You may wish to reference all the energies, asymptote the energies, which we did, and then you can use KJs or kcals, and I'll explain here why it doesn't really matter what unit you used, but then we're going to read the data in using a command, and that's why we need this file that we're using to be in the same directory as that book file, because that helps us out with reading in the data. And then we also need to make guesses on the fit parameters. When we do a nonlinear least squares regression analysis, we have to provide a guess for the parameters in order to get a reasonable fit. And so we're going to have to provide guesses, so I'll go through how we make our guesses. And some of them are pretty easy to guess, some of them a little bit more complicated. But then you want to read your results from the fit results once we get a good fit. And then what else here? You do not need any of the uncertainty values this semester, so we're not doing any of the error analysis you might find here. Okay, so what we're going to do is change our text name to book 1. I don't think capital letters matter, but I'm going to match it just in case. So book1.text. The fact that this isn't in red is good. If you see like the text in red, then that would mean that something's not being read correctly. Okay, so our data is being read in. I should be able to scroll down. I may need to adjust here. The adjustment, you see the labels here, the adjustment's right here. So we're gonna go out to, let's say 2000. I wasn't really paying attention to how high the energy went. That's too much. Let's go to 1200. And then instead of going to negative 200, maybe go to negative 10, because the energy's already zeroed out to 0. And then you can kind of see some of these parameters here, like our equilibrium bond length looks to be about 1.3 angstrom. So our guess parameters get put in right here. So these are the guess parameters. See how it says guess parameters. And so we can guess, and I should also point out, see the blue line, that's the fit. That's not a very good fit, so that's why we need to provide some fit parameters. And as soon as we get close enough on these, it's going to be good enough. And so the RE is the equilibrium bond length. The dissociation energy is dE. So the dissociation energy is where the energy is asymptoting. So where the energy is asymptoting here, minus our minimum point, which we've set it to 0. So if we didn't set it to 0, this might be a little bit, we'd have to get a calculator out maybe. But our difference here is 1200. So our dissociation energy looks to be about 1200, and our units kJs per mole. Here's where I made the program for kcal. So if you want to read your data in kJs, just change that to kJs. So we're reading these in kJs per mole, not in kcal, with the way we did it here. And then the con is the minimum energy point. And if you're not sure what these mean, the constant for offsetting the equilibrium electronic energy, i.e. the energy at the minimum energy point. So the minimum energy point is 0 for our data. If we didn't set it to 0, we'd have to look and see where the energy is bottoming out. It'd be a little bit harder to determine. So if you zero it out, it makes this fit a heck of a lot easier. Okay, so the fit is still not very good, which is a little surprising maybe. So the thing we might do is change the A parameter. The A parameter is the one that doesn't have a really good physical explanation. So it's really hard to kind of guess the A value. And this looks to be probably as good as the fit's gonna be. If you notice, like, we're missing the potential region, but we're matching here really well. And it's a give and a take. So in order to match this better, it's probably going to be off on these data points in a worse way. So the program's trying to reduce the linear least squares errors regression analysis to do the fit, and this is probably as good as we're going to get. We can try a few other things. Maybe we can make A a little bigger and see if that changes the fit. Usually once you're good enough to get, any kind of fit at all, that's as good as it's going to be. As I say that, maybe 0.02 on A makes this a little bit better, but you can play around until this fit looks to be about as good as you can possibly get it. So play with your guesses here and then read off your results here. So this is our dE and kJs per mole. This is the A parameter. The A parameter we're going to need because it has a relationship to the force constant, the spring constant for the molecule, sort of how broad this potential well is. The equilibrium bond length is, just what it says. It's the equilibrium. It's the point at which the energy is minimized for the molecule. And then the con, oddly, is reading a little bit higher than 0, but it's just the minimum energy point, and it's just one of the 4 fit parameters that we fit our data to here. Now, I can't remember if this is still part of this file or not. I think I deleted the next section. Okay, so that's all for this particular file. This is some error analysis jargon that we don't need for our analysis. So we really just need these fit values here that you can then take the A value, do some arithmetic to figure out the force constant, and then we can also take then the force constant, determine with the reduced mass, we can then determine the fundamental vibrational frequency, and then from there, that's probably about all we're going to do this semester. There's a few other ways you can make connections between some of these results and some of the values you might look up on the constants of diatomic molecules. So in a nutshell, the idea is to start with an Excel file with your data, minimize the energy to 0, find that minimum energy point, set your data to 0 so that all other values are higher energy from the minimum point, and then use a unit of kJs or kcal per mole. Either one works just fine. Just know whatever unit you convert to and make note of that as you do the experiment. All right, that's all for the video. Thank you.